So in this session, I'm gonna use the OpenStax 5.126, the last problem on the chapter, to talk about charged rod. I find this problem very interesting, so I could start after you look at the questions. So I changed a little bit. I added this part to find the potential at Q, and I find it very interesting to connect between the electric forces and the potential, so I'll explain a little bit more. So first I define a Cartesian coordinate systems on the charge itself. So here I have negative r comma 0, r comma 0, 0 comma r as three points to verify my coordinate system. I included this data so that we could use polar coordinate later, because this question is very intuitively to use polar coordinates. And so we could get started with finding the we could do with the potential first, and then we could do the electric forces. So let's get with the potential at Q first. So first I set up this equation, dq equals to lambda dl. Lambda is the charge density on the length of the wire. So I'm talking about at this point dl, there's a little charge dq, and the dq is given by taking the lambda, which is the unit charge, times the dl, because the unit charge is saying charge per unit. So if I'm saying that I'm trying to find the little charge on that little distance of the wire, I have to use lambda dl. And L is just simply 2 pi r divided by 2. So because this is a semicircle, a full circle would be 2 pi r, and I've divided by 2 to get pi r. So dl is equals to r d theta. This is just by mathematics. So if I have the dl here, I'm talking about this little length. I'm trying to convert dl to d theta, so I have to use some trigonometry to get this equation, dl equals to rd theta. So after that, I have the dq equals to lambda rd theta. And here I'm trying to say that this part is actually corresponding to the E field over here. So I'll explain that later. So first I set up this equation, dv equals to the Coulomb's constant with the dq over r. This is the standard step of finding the potential with some symmetrical things like this one. So after that, I'm just expressing dq in terms of lambda rd theta. So I cancel a little bit things. Up to this point, this is the differential equation for my system. So I just have to integrate both sides. So after I integrate both sides, I'm using the polar coordinate system to find my potential. So at this point, I'm still talking about one little point called dv. But at the next step, I'm talking about all of the points summing up here, the whole circle. So after that, I have this expression here, and then I have this one. This is my final potential for the system, lambda over 8 epsilon naught. And it is really interesting because I don't have to go through all the process. Instead, I could just use the formula that I have for the ring. The ring is this one. So this one's the full ring. The full ring have the equation as v equals to 1 over 4 pi e naught q over r squared plus z squared here, where this time z is equals to 0. So if I do a little bit algebra, I could get to this form, 1 over 4 epsilon naught lambda. And notice how these two are relating to each other. So it only differ by 1/2, which makes sense because if I just cut the full ring into half ring, then I should have half the potential. Now I have to do the electric forces at Q, which is what the problem was asking originally. So here I'm just trying to sum up all the electric forces to find the electric forces on Q. So if we take this point here, the electric forces will go in this direction. If we take this point here, the electric force will go in this direction. And by symmetry, these two electric forces should cancel out. But this one cannot be cancelled out, and this one electric forces will go into this direction. So in a sense, we will predict our answer should be in something negative j. E is equals to something negative j. And this is the things that I'm talking about here. So if I separate E into EX, EY, and EZ, EZ is equal to 0 because simply there's no electric forces on the z-axis, and EX is equal to 0 because all the electric forces on the x-axis are cancelled out because of the symmetry. So here, after I expressed E in terms of this equation, which is very standard by the Coulomb's law, I expressed my r hat in terms of the Cartesian coordinates with theta here. This is something that I struggled with when I was doing this question. But and notice I put the negative here because the electric forces are repulsive with the positive charge here. And the direction would go to negative j instead of positive j. So I have to put a negative here to make sure that I get the negative j at the end. So I just have to, here I have to integrate. Here I have to integrate both I and j with respect to 0 to pi at the angle. And this expression would give me negative 2j. So all I have to do now is when I sum up all the electric forces, I'm just summing up the magnitude times negative 2j. So at the end, here's what I said, and at the end I will have this form after I substitute different things with these three equations. So after I found my electric forces in this form, and I compare with the potential energy, which is this one, I find it very non-intuitive. Because I know like electric forces is just the differential of it's just a negative differential of the potential energy. And since there's only electric forces on the y-axis, what I originally thought was if I integrate this electric forces, with the y-axis, so I have to integrate with dy, and the y is from 0 to r. Well, I eventually get negative lambda over 2 epsilon naught. And this is not the same result I get from this one right here, which is lambda over a epsilon naught. Oh, I have to put negative, so this one is, the negative will cancel out. And this is not the one I have if I do the approach in here. So I thought for a while and I realized my mistakes. And my mistakes is that the electric forces on the x-axis cancel out, but the electric forces on the x-axis will create some potential that I didn't account for. So right here, if I integrate this one is only the this one is only taking account for the potential on the y-axis, but there's also potential on the x-axis I didn't account for. So if I take account, so this part is equals to 0 originally, so if I take this one, instead of doing it 0, I do it from 0 to pi over 2 cosine theta d theta I integrate this thing. This should get me this should get me negative sine theta from pi over 2 to 0. So this one is equals to 1. So if I do the electric forces with this segment, then so if I do with that segment 0 to pi over 2 instead of 0 to pi, and I multiply my result with 4, this should give me the full range of this constant here. And I think this is very this is very interesting, and I carry that in my mind after doing this problem. So I hope this problem explained how the charged rod with the charge density work. Thank you so much.